do the recording. Yeah. Thank you, Prince. Thank you for reminding me. Okay. So let me redo this part since it wasn't recorded. So I'm going to calculate and then you figure out whether you have done it correctly or not. So first of all, you get the predicted values and actual values. Here also you'll have the predicted values and actual values. Let's go to the first row. The value here is 5. 5 is less than or equal to 5. So the predicted value would be yes. Actual value also is yes. Then let's go to the second row. The value is 1, which is less than or equal to 5. So the predicted value will be yes. And the actual value also says yes. Then we go to the third row wherein we have 5. Less than or equal to 5 would be yes. Actual value is also yes. Then let's go to the fourth row. We have 5. Is 5 less than or equal to 5? Yes. So the predicted value will be yes. Actual value is no. There is a mismatch. Now let's go to the next row where the value is 10. 10 is greater than 5. For greater than 5, the predicted value would be no. But what does your actual value say? That also says no. There is a match. Now let us calculate entropy towards the left and entropy towards the right. Left side is this. Okay. So less than or equal to 5. Okay, that's your left side. So less than or equal to 5, you'll have 1, 2, 3, 4, all these 4 values. Okay. And then what would be how many y do we have here? 3 out of 4. And how many no do we have? 1 out of 4. So here, going by this entropy formula, since you have 2 classes, yes and no, you write this as minus summation of I equal to 1 to 2 probability of xi into log of probability of xi base 2. When you substitute I equal to 1, you get minus probability of x1 into log of probability of x1 base 2. Again, minus. When you substitute I equal to 2, you get probability of x2 into log of probability of x2 base 2. Probability of x1 is 3 by 4. So you get minus 3 by 4 into log of 3 by 4 base 2 minus x2 is 1 by 4 into log of 1 by 4 base 2. How much would you get when you solve this? Let us solve this. It would become minus 3 by 4 into log of 3 by 4 base 2 minus 1 by 4 into log of 1 by 4 base 2. And then you get how much? 0.81128. This is going to be a probability towards the left. Okay, let me write it as 0.81128. Now let's calculate probability towards the right side. So the left side part is done. Let's calculate the probability towards the right side. On the right side, it is only greater than 5. Greater than 5, how many do we have here? Greater than 5, you have only one entry because we are doing it for price. Price greater than 5, how many do we have? Only single entry. So take this one. So what will be probability of y? How many y do we have here? 0. 0 out of 1. And how many no do we have? 1 out of 1. 1 by 1 is 1, 0 by 1 is 0. So how do you write it as? Minus 0 into log of 0 base 2 minus, you have 1. 1 into log of 1 base 2. 0 into anything is 0, minus 1 into log of 1 is 0. So overall you get 0. Correct? So entropy towards the right side is 0. Now what are we expected to do? We need to combine left and right side. In order to combine these two to get entropy after, on left side, how many do we have? 4 out of 5 entries. So 4 out of overall 5. So I write it as 4 by 5 into entropy towards the left. Entropy towards the left is 0.81128 less. On the right side, how many do we have? Only one entry, 1 out of 5. So 1 by 5 into entropy towards the right side was 0. So 1 by 5 into 0 is 0. What will be 4 by 5 into this? Let's calculate. 4 by 5 into 0.81128. When you solve it, how much did we get? This is what? Entropy after. Okay, so we got entropy after as 0.64902. And what is entropy before? 0.97095. When you subtract these two, you get information gain for price. So let me do that. This value minus, not this, sorry. You should get 0.32193. Okay, this will be the entropy after. Now, after this, we'll run the code and then we will jump into the other discussions pertaining to the other Ensemble techniques. Before that, let me look at 2 questions, 3 questions. Okay. Shouldn't we convert continuous features to discrete? Yeah, you have to convert them. Or leave it to decision tree algorithm and that would automatically convert you. Point number 1. Okay. But here we are not doing it. Okay, that's fine. I'm leaving it to the algorithm to convert. But I'm treating these as objects. Count, categorical count it. Okay, Ali says, for every entropy before and after, we will get 0. Why will we get here? We didn't get, right? We got a different value. Hope that answers your question. Now, yeah, our friend had a question. Yes, please. Predicted value will be, condition will be. Condition is less than or equal to 5 and condition is greater than 5. That's a rule. Okay. Yeah. Based on that prediction, you got the value as no. I don't know to what extent I can go back, but let's see. That's it, I think. Okay. Tell me, go ahead. So there is a specific column called as price, which is a feature in which we are having a classification rule, which is less than or equal to 5, greater than 5. For less than or equal to 5, I'm saying yes, it'll be useful for play. Greater than 5, I'm saying no. What is your question? Do you have any doubts here in this rule? Yeah, in this rule only. Yeah. In this rule, do you have any doubts? That's the question that I'm asking. In this rule, do you have any questions? No, fine. Yeah, next. Okay, in serial number 4. I have 5, which is less than or equal to 5. So what will be the predicted value according to this rule? Yes, wonderful. What is the actual value? This is actual value given to you by a customer. Yeah, obviously. No, why will you take this? This is the prediction. Actual is given in the data, right? Whatever is given to you by the customer is actual value. No problem. Clear, right? Okay. Hold on. We'll get there. Venkatesh, we'll get there. Hold on. Okay, first, let's complete this. Okay. What do you mean by greediness, Venkatesh? Okay, let me unmute Venkatesh because Venkatesh feels that he asked me this question twice and again he might be offended. So Venkatesh,
No, sir.
yeah,
I was just curious.
yeah.
That's
So
all.
what do you mean by greedy? Are you a greedy person, Venkatesh? If I give you
Greediness.
two job offers,
Uh-huh.
in one job offer, I'll say that I'll pay you 10 lakhs per month. And in
Hmm.
another job, I'll pay you 2 lakhs per month. Which one would you choose?
10 lakhs.
So you're a greedy person, right? On similar lines, why is
Uh,
decision tree called as greedy algorithm? Because when it does that split, is it
mhm.
choosing that variable which has the least information, or is it choosing that variable which has the highest information?
Highest information.
Oh, you're going with highest information. That means you're greedy. Like salary, I go with the highest salary, right,
Mm.
Venkatesh?
Yeah. Yeah.
That's the logic behind naming this as greedy algorithm. Simple. There's
Okay.
no
Okay.
extraordinary reasoning here, right? Simple. Lazy. Lazy algorithm is KNN, K nearest neighbor. Why is it called as lazy algorithm? Because it's like students only. When I say tomorrow we have, or if I say that exam will be on 31st August, when do you end up studying? On 30th or on 31st morning.
Yeah.
KNN algorithm is also like that. When you give a new entry and say predict,
Hmm.
KNN will then start calculating the distance between that new entry to all the data points.
Okay. Okay.
And then it will give you the result. So it will not already calculate and keep it, in the system because that provision is not there in KNN. Only when a new entry is given, new inputs are given, it will take those new inputs, it will calculate the distance of that new record or new set of inputs to each and every data point that you have to find the distance,
Right.
right? And then to whichever it is closest, it will assign that particular class. That is
Okay.
the reason why it is called as a lazy algorithm, because it will do only at the last minute.
Right. Yeah. Thanks, sir. Thanks.
Yeah. Yeah. Oh yeah, it will recalculate. Now, not just different k value. Say you trained your model, you kept it with you, job done. Now, if I give a new entry, what it will do is with that new entry, it will calculate the distance. If you have 1,000 training points and one new entry, it will calculate the distance between this new entry to all the 1,000. And then if you say k equal to 5, it will choose only the 5 nearest distances. And then for those 5, it will look at what are the classes. And the majority is what it's going to assign. When you say k equal to 7, out of all those, it will pick the top 7. But when will it do that calculation? When you give a new record and say, tell me whether this new record belongs to A or B, then it will do the calculation. K value is only used to choose from those. Okay, probably when we talk about KNN tomorrow, if I'm not mistaken, then we'll get it.
This problem, all the balls are the same.
Hmm.
It's 5 balls are different. We can
Hmm?
we can calculate.
I didn't get you. Come again. Sorry.
In this problem, all the balls are the same.
So first talk about this one. All the balls are in
Same.
red color. So talk about only this. One after another. So we have ball color. And what are the two classes that you have? Yes and a no. Tell me. If it is red color, should be yes or no? Why yes? We also have no, right, for it. Either it is red color or not red color. That is what you'll have. I got your question, but first let's solve this. Now you go ahead with the first entry. Is it red? Red is this side. So predicted value will be, actual value is also second entry. Is it red color? Predicted value will say yes. Actual value will say yes. Is this third entry red color? Yes. So the predicted value will be yes. Actual value is also yes. Is this red color? Predicted value will be yes. Actual value is this red color? So predicted value is yes. Actual value is no. For it is not even going into this, not even needed. So here you calculate your entropy after. Okay, entropy after means you choose everything now. Once again, you choose everything. When you choose everything for entropy after, because there's no left and right. So you choose everything. When you choose everything for probability of x1, which is yes, how many yes do we have? 3 out of 5. P of x2 will be no. How many no do we have? 2 out of 5. When you solve it, do you know what you'll get? You'll get the value exactly similar to entropy before. And what is information gain? Entropy before minus entropy after. And entropy before minus entropy after, what would you get? So do we have any information in this? No. Now tag it back to the discussion that we had in the very beginning of the training, wherein we spoke about exactly in data cleansing, we discussed about something called as zero variance or near zero variance features. What did I say at that point of time? If you have a variable wherein every value, if it is the same, you just remove it. You need not have it in your training. Oh yeah, you remove it. That's it. You need not even do all these things. I have a variable, every ball color is the same, just delete it. Now going back to your question. Our friend is saying that, no, this part I understand, but what if we have blue color and what if we have black color? Now we have 3 classes here and a ball color. Now I have yes and no is what I need to classify, but then I have what? Red, blue and black. So we have red, blue. For 2, you told us how to solve it, but what if I have 3? Then you can say red, blue and black. One rule. Then blue, red, black. Again, solve it like this. And then you'll have black, red and blue. So you have 3 different conditions. Okay, same yes and a no. Yes and no will be the same. Okay, yes and no will be the same. If it is red, yes. If it is not red, that means if it is blue or black, it will be no. For this, you calculate the entropy. Then calculate the entropy using this rule. Blue means yes, red and black means no. Calculate the entropy. Then black means yes, red or blue means no. Calculate the entropy. Whichever gives you the least entropy, least error, take that as a rule and proceed further with your calculation, entropy after calculation. Making sense? Okay. Nothing like that. No, there is nothing like that. Are those classes going to give you the right classifications or not? That is more important. That means, would it give you the right classifications here? That's important. The number of classes that you have in the variable doesn't matter. How are those rules related to this? Yeah, entropy will be, information gain will be high. Yes. That's the same formula which is given here. Total number of classes. We have done that, right? 3 by 5, 2 by 5, that is this. Into whatever is the information that you get. Then when you subtract both of these, that is entropy or expected information, before versus after, you get the information gain. Okay. If you take this example, for that example also, the calculation is just given. You can look at that. Same thing, but 14 records. Okay. So you get all this information gain, and then which node would you choose as a root node? The one which has the highest information. And which one has the highest information? Age. So it chooses age. Okay. So in that way, the split happens, and then you get different classification rules. Okay. There are certain disadvantages with decision tree. And the first disadvantage is that it has access parallel splits. Meaning, say there are two variables or features that you have. One is A-list celebrities. A-list celebrities. And next thing is estimated budget. And then you want to come up with an output, whether it's a super hit movie or just a hit movie or a flop movie. In that way, you want the information. So you have three classes. Red is one class, green is one class, and blue is another class, assume, right? These three classes. So what will happen is, to split the data, it will only be able to come up with the access parallel splits. So when you want to use A-list celebrities, it will come up with a split like that. And if you use estimated budget, it will come up with a split like that. What does that mean? These values will be misclassified. Okay, these values will be misclassified. Whereas if you look at a few other algorithms, what they do is they come up with a split like this. Okay, and maybe like this. So what will happen? Anything which is below here will be red. Anything above that would be green. Anything which will fall here would be blue. That is how you split. Okay, but when it comes to decision tree, this flexibility is not there. Whereas the other algorithms can come up with this kind of a split. Since that flexibility doesn't exist, and since decision tree can do only access parallel splits, I mean, this split is parallel to x-axis. This split here is parallel to y-axis. So you're restricting yourself, you're forcing yourself to do only certain predictions correctly. In the good old days, people started off with ID3 algorithm, iterative dichromatizer 3. Then slowly they moved towards C4.5. Then slowly they have upgraded to C5.0. 5.0 is an algorithm which was developed by Ross Quinlan. And the multi-processing capability, he's selling it. That algorithm is being sold by this guy. You need to purchase a license to be able to use that. And to split, we have used entropy, right, as a thumb rule. Alongside entropy, we also have Gini index. We also have chi-square statistic, and we also have gain ratio. These are the other splitting criteria which is available alongside entropy. It's not just entropy, you also have Gini index, chi-square statistic, and gain ratio. This is just the old decision tree algorithm name was ID3. Then they named it to C4.5 and they put some additional information. They enhanced the algorithm. Then now the current algorithm is C5.0 from decision. These are different versions. Like you have iPhone 12, 13, 14 coming up on September 7th. Okay. Then how do I avoid overfitting? Overfitting or the regularization technique. I would say regularization techniques which are used to avoid overfitting or underfitting are called as pruning techniques. Pruning. The moment you avoid overfitting, you're generalizing your model. You're making your model very generic for the future data. That means even if you have slight changes in your future data, it will work well. That is what is the meaning of generalize. Okay. So one is called as pre-pruning or early stopping. You put certain conditions and you say that please do not grow further. For example, if you say maximum depth equal to 1, do you know what will happen? If you have a root node and if you're splitting it, that's it. It will stop here. It will not split any further. It has reached depth equal to 1. Depth equal to 1 is also called as decision stump. Depth equal to 1 is given a special name called as decision stump. Okay. Next, you also have something called as minimum samples split. So if you have to split it further, in this, say you have 1000 observations. When you split it, maybe you have 500 observations here, another 500 observations here. If you say that minimum split and you're splitting it further, say here, you have now 200 and here you have 300. Okay. Now, if you say that minimum sample split should be 250. Minimum samples for me to split should be 250, meaning minimum I need 250, otherwise I won't split. Would it split here? No, because you have less than 250. Would it split this branch? Yes, because you have more than 250. Then you have minimum samples at the leaf node. Leaf means last node. You can say equal to 3. That means even if you have 3 nodes, it's 3 records, it's going to stop. It won't go by our rule. What was our rule? Continue splitting until all the classes are the same or you have a single row. It won't continue splitting because you're putting a condition. Stop. If you have 3, stop. That's the condition. Okay. Then you have something else which is called as minimum impurity decrease. What is impurity? Entropy. When you continue to split from here to here, when I split, is that specific entropy? I mean, you can put a condition. Minimum, I want 3% reduction. 3% means 0.0. Minimum, if there is 3% or 10% or 20% reduction, only then continue. Otherwise, stop. So you put here 0.03, but here from this level to this level, entropy reduction is say only 1%. So it will not split. We'll say that doesn't make sense because its minimum reduction is not available. Okay. Same is the case with minimum impurity split. If you have minimum of 10% impurity or 20% impurity, then split. Okay, so these are the various rules that are available. All these are called as what? Hyperparameters. All these are called as what? Hyperparameters. If I say maximum depth equal to 1, if you are splitting the tree, what is the depth here? Once you split, done, it will stop. Maximum depth equal to 2 means it will do the split twice and then it will stop. One split, second split. Okay. Then we also have something called as post-pruning, right? Post-pruning means let the tree grow completely and then apply your rules on that. It will not stop prematurely. It will continue to grow completely. And then you apply the rule. Minimum, if the error value is less than some number, you stop. Then what will it do? It will go there, go up. Then that's post-pruning. Apply the rule. Yes. You will see that, you know what? Only if somewhere the error rate is so much, right? Less than so much, you have that branch. Otherwise, remove that branch. That's called as grafting or subtree replacement. Grafting or subtree replacement. Okay, so do we have anything else here? No. Now, hope you all understand greediness. Hope you all understand information theory through entropy, etc. So now we should get into the code part. Yeah. A different set. The different set are available. So whichever you feel is part of pre-pruning, it's going to stop your algorithm, so be it. So when you grow your entire tree completely, right, you can also say that minimum impurity decrease or minimum impurity split is something that I want to apply. You can still apply. That would be called as post-pruning. So certain regularization techniques can be both helping you perform pre-pruning as well as post-pruning. Very good. Yep. Here we have decision tree code and decision tree datasets. Okay. There are two use cases here. Both of those we'll discuss. One is for classification. Another is for regression. So in this case, output variable will be categorical. What happened? So let me open Anaconda. And come on. I'll launch Spider. Because Spider gives you a lot of options, right? When you load a data set, immediately you can double click on that, open that, see what are the various variables and all that. That's why I prefer this. Very good. Okay, so we will proceed further with this. No. Yeah, with this. But before that, let's take a quick break. We will take only for 10 minutes and then we'll come back. Let me stop this recording.